Okay, so we'll start now. Let me just check if Okay, so there are no messages that anybody's facing trouble joining. So we're meeting after a long gap. So we have done three classes so far. So we're studying antennas and radiating systems. This is the outline, and we have covered till thin linear antennas in the previous class, and today we'll cover antenna arrays. And we are referring, just to remind if anybody is joining new, we are referring DK Cheng, Field Wave and Electromagnetics. So it's very important that everybody has this book because we'll see some examples from this book today, and some of the examples will be left as assignment, and the solutions will, since they're examples from this textbook, the solutions will be available here. And if you like, I'll discuss them, and if it's like, and you can go back to the book and try doing them yourself, and if there are any issues, we can discuss them in the next class. And if you want to go in greater detail, the you can refer to Antenna Theory by Balanis. um, okay. And the previous class, we covered thin linear antennas, half-wave dipole, and effective antenna length. And based on the the text that we discovered in the previous class, will study antenna arrays. Today, we'll begin with two-element arrays and then discuss general uniform linear arrays. Okay, so we're discussing arrays today, and the antenna arrays are groups of similar antennas which are arranged in various configurations. So let me just use a pen. So essentially, for example, if we have some kind of antenna, let's say we have a patch antenna, and this radiates, right? But what if we want some customized pattern, or we want a higher gain, or some sort of other function? So what we do is, for example, this antenna is being fed like this. What we can do is we can have two patch antennas, and then we can feed them together. And what we can also do is, maybe we can have a patch antenna, and then we can have another patch antenna, and this is fed at this is fed like this, and the other one might have some phase delay as well, and like this is the feed over here, and over here they are being fed at same phases. And what now we can over here have some I1 plus delta of 2. So they can have different phases as well, and we'll discuss about this phase delay and stuff in the coming slides. So what we can do is we can have multiple antennas, and they could either be similar antennas, they could also be, we can have one patch antenna and one dipole antenna being fed. So we can have different types of antennas radiating together to achieve certain patterns. So this is what is meant by arrays. So if you have done any data structure classes, or like for example C or Python, if you do coding, so arrays are essentially a series of elements. So similarly for antennas also, if we have a series of elements being smaller antennas or similar antennas, we form arrays, and using these arrays we achieve some desired functions. So antenna arrays are a group of similar antennas arranged in various configurations. They could be straight lines, circles, triangles, and so on. So But when we say straight lines, it could be, for example, we have one antenna over here, these extra antenna like this, and we could be at some distances. So this is like straight line, or we can have array arranged in a circular fashion at some distances and at uh, some angle. So triangles and so on. So like we can arrange them in different ways to achieve different patterns or some relations, and they could be with proper amplitude as in. So we can have similar power delivered to the different antennas, or we can have different power delivered to each antenna, and phase relations. And so, as we talked over here, we could have them different phases, or we could have same phases, the power which is being delivered to them. So, based on the power which is being delivered to the different elements, or the phase delay between the elements, or how the elements are arranged, and then we can form different antenna arrays. The radiation characteristics. So the frequently the radiation characteristics of importance are the direction and the width of the main beam, side lobe levels, or directivity. So for an antenna, we had discussed the antenna parameters, which were the direction and width of the main beam, which we have discussed, and then there were side lobe levels or directivity. So one of the important functions of forming arrays is getting a higher directivity. For example, if you have a monopole, so you'll have some this kind of radiation pattern. For example, if this is like broadside um, radiation, but what if you want a higher directivity? So we can use arrays to get higher directivity. We can, if we want up like more like we want a lesser beam width, or like so for that also we can have arrays, and we can reduce this beam width again. So all these things can be handled by forming antenna arrays. So we'll start with the linear antenna arrays, and then we'll briefly uh, generally discuss what if they are not linear, like that is not in a straight line, or if we are forming 2D arrays and stuff. So that will all be discussed later in this particular class. And one important thing is that we'll be using vector superposition of fields produced by individual antenna elements, and this will give us basically uh, the desired like the desired output, the desired parameters that we want to look at. So the reason we are forming arrays is that we want to modify the beam width, or the side lobe level, or the directivity. And for all this, we need the radiation pattern. For example, if there is some antenna, patch antenna with us, and we have this radiation pattern with us, right? And we are forming arrays, and now we need the radiation pattern of this antenna array system. Now, so we need to form this antenna array system, and if we have two radiators, and we start finding the electric fields with the two radiators, it will be a more complex problem. So what we'll do is we'll take the electric field of both the radiators, let's say E1 and E2, and then we will E1 and E2, and then we'll trust that principle of superposition works, and then we can find out the electric field at uh, for example, the electric field due to this patch is E1 at this particular point P, and then due to this patch is E2. And then we'll say that the principle of superposition works, and then we have the total field at this point as which is E total equals to E1 plus E2. And so this, and if we generalize this, if we have we have n number of antenna elements, so this will imply that for each we can find out the vectors superpose vector sum of all the electric field due to each element at this particular point, and then we just add them and we get the total electric field. So that's the idea. We'll be using vector superposition to find out the electric field at that position, and then hence the uh, 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 and hence the uh, radiation pattern and rest of the other parameters. We'll start with the simplest case of two element arrays and then generalize. And once we have some experience, so the two element array that will start will have identical elements. So let's start with that. So this is the figure 11 9 from the textbook, and where we have two antenna elements over here, 0 and 1. So we have the two antenna elements over here, and we will try to find out the electric field at this point P over here. And this particular point P is at a distance R naught from element 0 and R1 from the element 1. And this particular P is far away from the, so this is in the far field of the of both the antenna elements, and the elements are separated by d distance. And this particular angle, if we look at, is the yeah, this angle is phi 1. So this is the setup, and now we'll try to calculate the electric field at point P. And other information is that the current in antenna 1, the phase in antenna 1 uh, uh, leads by phi phi angle. Sorry, xi angle. Yeah. So this will have a phase shift of xi. I'm hoping I'm saying the correct alphabet name. So these are Greek alphabets, and I'm a little confused with what we call xi and psi. And, okay. Okay. So this particular element has a phase difference of xi, and so we can write the electric field like this. So if you remember from the previous class, this is the element factor, or the field, yeah, the field fact, yeah, the pattern function, yeah. Okay, so this is the pattern function for each this Hertzian uh, dipole antenna. So we are over here we are considering these are Hertzian dipole antennas, which uh, we had derived the electric field equations, and especially in the far field. So the far field expression, and then the previous class we had replaced the dependence from theta and phi as which was a pattern function is written over here, and this changes based on your based on the excitation of your antenna. So E naught at this particular position due to the first element is written like this. We have electric, and we have the magnitude as EM, pattern function F theta phi, and since both these elements are same, we will have the same magnitude and the pattern function. And then we said that the second element has a phase difference of xi. So this is xi over here, which is added to the phase distance, and both are at distance r naught and r1. So r naught and r1 over here. So we can write the electric field at this distance, at this particular point P as E0 and E1, and then we'll use the vector superposition over here to find out the total electric field. So the total electric field will be E is equals to E0 plus E1. So we are calculating the total E as the sum of these two electric fields from the elements 0 and 1. And taking the common factor over here, we end up with these two elements over here. Okay. So now we have the electric field written in this form, and now we need to simplify. So we'll use some approximations. The first one being, since the distance r naught is much greater than this d by 2. Uh, so this 1 by r1, which is over here. So this 1 by r1 can be can be interchangeably written as r naught as well. So this r1 and r naught, they are like kind of similar. Like their magnitude is very similar as compared to this d. Like this d is very small, so these two are approximately equal. So we can just replace r1 by r naught, and but the since both these elements, uh, since r naught and r1 are also in the phase term, and over here this the even the smallest difference might affect the total field over here as constructive or destructive addition. So we won't just change r1 to r naught over here. So we'll use a better approximation here. So so taking like if we look at this particular, sorry, if we take a look at this particular triangle over here, so uh, this is did I miss something? Yeah, this becomes r naught d sine theta cos phi. Okay, some where did the theta come from? The theta direction and the antennas are. I'm missing something. I'm not sure where did we get the theta from. Like theta family. Okay, I'll come back to this. This should have. We're using this approximation. I'm not sure. I'm missing something. Okay. We'll discuss this later. Let's just take this for now. That this r1 is can be written as r naught minus d sine theta cos phi. This has something to do with this scalene triangle thing, that we have some angle over here, and then we have the this distance as d, and these two distances r naught and r1, and we end up with this thing. So this is some approximation. This is some mathematics which I'm sure that there's something wrong with this figure. Uh, we'll discuss this later. Let's just take this for now. So we're using an approximation to find out an approximate value for r1, which is r naught minus d sine theta cos phi. So this particular thing is phi over here, and I don't see where this theta came from. Let's just stick with this and later figure out how did we get this approximation. Anyways, so we use this approximation again in this expression over here in the phase term, and not in the denominator term, and we'll end up with this particular expression over here. So the E field is now E power minus j beta r naught. So we have not now written the r1 as r naught minus d sine theta and cos phi. And once we have written that, we can separate the e powers like this, and we get the we can take out the this particular term as common over here, and we end up with 1 plus e power j beta d sine theta cos phi and e power j xi, j xi, which is over here. So we got this expression over here, and now we can simplify this further. So if we take, so what we do is we take this entire argument, these two things, we can like these are both of them have the same base, so the powers can be since they are in multiplication, the powers can be added, and we can write this as this this phi over here. I think this is capital phi. So I'll just say capital phi for now. I don't recall the correct Greek alphabet name. Um, if somebody remembers this, please let me know. Okay, so this capital pi over here, and then so once we have replaced this thing, so this is 1 plus e power pi here, and we can what we can do is we can write this as e power 5 by 2 e power minus 5 by 2 plus e power 5 by 2 multiplied and divide by 2 over here, and this particular thing becomes cos 5 by 2 into 2. So this is basically writing the cos function in terms of exponential. So that's what we have over here. And since we took this e power capital pi by 2 outside, so we have this term over here. And this was the other uh, exponential term. So we now have electric field as this expression over here. So we've got the equivalent electric field over here now. So if we take the magnitude of this term that we got over here, we're taking the magnitude. So if we take the magnitude, these terms do not the magnitude is 1 because they are complex terms with j over here. So they do not contribute to the magnitude. So the magnitude is it's yeah. So we're taking this 2 em f by r naught term over here, and then we take the magnitude of the pattern function and the magnitude of this cosine over here. So this f naught can now be called as the element factor because this comes from the individual element over here, and this particular new term, which is due to the combination of these two elements, can be called as array factor. So we have now two quantities which are dependent on theta and phi, and they are the element factor and the array factor. The element factor derives directly from the element, and the array factor is dependent on uh, the element factor. The array factor is not dependent on this the beta term, which is basically due to the wavelength, this d term, which is the separation between the elements, the theta and phi terms due to uh, the position of the point where we're trying to figure out this electric field. The coordinate system basically is, so we have uh, so if this is z over here, this is x, and this is y. So um, this is theta and this is phi, right? So so based on this elevation and the azimuth angles, so we get the position of P, and based on that, the fields will change. So we have theta and phi, and then the xi is the phase difference between the first and second elements. Okay, so we have now written the electric field expression due to the this array arrangement over here. So the element factor is the magnitude of the pattern function of the individual irritating elements. So that's the element factor, and the array factor depends on the geometry, which is as well as the excitation. The geometry is given by this D, and the relative amplitudes as yeah, over here, since we have taken identical elements, so we do not have any relative amplitudes, and then phase excitation is given by this xi over here. And yeah, so the array factor is that of an array. So this array factor corresponds to an array of isotropic elements over here. So we took isotropic elements over here, and their properties are already included by the element factor. So if we change the elements over here, uh, it will be reflected in this term over here, and the array factor would remain same because this array factor is only dependent on the phase excitation and the geometry. So if we change the position of the elements, that will affect only the array factor, and if we change the elements individually, that will affect the element factor. So any change in the type of antenna won't affect the array factor over here. Yeah, so from this expression, we can conclude that the pattern function of an array of identical elements is described by the product of the element factor and the array factor. That's like pretty much visible from this expression. So the pattern function of this total system is now product of these two. This is now the new pattern function for the array. Earlier, the pattern function was the element factor for the individual elements, but now the pattern function is the combination of the element factor and the array factor. And this property is called the principle of pattern multiplication. So what we are saying is that we take the individual pattern of the elements, and for both both the elements over here, or if we have more elements, so we take the individual pattern functions and then multiply it with the array factor. But the array factor is calculated on the basis of the geometry of like the arrangement. Using the arrangement, we get the array factor, and when we multiply them, we get the total uh, pattern function of the array, and this particular property is known as the principle of pattern multiplication. So um, so let's take an example. From the previous class, we had derived the electric field due to and the pattern function for z-directed half-wave dipoles. So now we are using z-directed half-wave dipoles at both the elements over here. And so in the previous class, we had derived this expression, and for the z-directed half-wave dipole, this was the pattern function. This was what we derived. So now we can substitute this over here, and this is the electric field expression uh, for a two half-wave dipole configuration, which is separated by d, and then the excitation as the phase delay is xi. Now, this particular uh, psi function over here. Okay, yeah. So I remember this is called psi. Uh, I think it's written as psi maybe. This thing, yeah, psi. This thing is said as psi xi. Yeah. So this psi, since this psi is a function of both theta and phi itself, so it will keep changing for different. Just Yeah, sorry. So this psi is itself now a function of theta and phi, right? So it's a function of theta and phi. So this will have like this will have effect. So we'll have this pattern function different from the individual dipoles, and if we see the E-plane of this particular configuration over here, it will not be same as of the single dipole, except in a particular case, so which is where this psi becomes pi by 2. So if this psi becomes pi by 2, this cos will become 0, and then this psi will only be equal to this xi function xi over here, which is now a constant value, and at that particular point, this will reduce. This will go back to the. This will resemble single dipole. So in a particular case, this might resemble the single element, but otherwise the single element and the array will do not have the same pattern function. And if for the H plane, for that is theta equal to pi by 2, the pattern is determined entirely by the array factor over here. So in this case, if you put theta is equals to pi by 2, if you put theta as pi by 2 over here, this psi will become beta d cos phi plus xi over here. So based on the theta and phi value, it won't match the pattern function of a single dipole. So the pattern function for a single dipole is not same as array. So we'll start with an example over here. I'll just pause if there are any questions apart from the approximation, this which I missed somehow. Like this approximation is something to do with maths, which I don't recall. But apart from this, any other questions? Okay, so I recall this, but I'm not able to draw the figure correctly, like properly, which I can make this, which can make you like visualize this. So essentially, what this point is, this particular point is, if we take the coordinate system like this, and this is your x coordinate, this is the y, and this is the z, and then there is a point P somewhere here, and we have the first element at the 0, and then the other element over here. This is 0 and this is 1. and this is at a distance d between these two, and this particular P point is somewhere in space. So if we join these lines and we take the projection of P on the x and z plane, and we take this particular angle, so we have some theta angle which is made over here, and then some phi angle which is like this. So using these projections, we we have to calculate this, like we have to approximate this R0 and R1. So I hope like I'm trying to explain like this more clearly. So we have some R0 and R1, and this particular P point is not in the XY plane. So this is somewhere in XYZ, uh, like in the space. So we have some theta and phi angle which is being made. We are making to reach this particular point P. So this, but we have this D which is along the XY plane. In the in the X or along the X-axis we have D. So we have to take two projections which are like sine theta and cos phi to reach this point. So we take uh, yeah, so this particular length over here some, so this becomes yeah, cos, somewhat this angle we have to make. All right, so we have to take some cos phi over here, and then we take us take then we using this we take some sine angle as well. So that's that's how we are achieving this. So we have like we have to write, like make a proper figure, and then we can get it. So that's what I'm trying to say is like we are taking two projections to get these two angles. So this is just coordinate geometry, and then like using that we can write this expression. So not this one, sorry, this one, 1180. This is some math and coordinate geometry. We just need to find out the correct projections in the space to approximate R0 and R1. Yeah. Okay. So uh, no questions. So no questions will proceed. Feel free to stop me and ask the question or raise your hand. So let's solve an example over here. Um, so we have to plot the, so this is H plane. We have to plot the H-plane radiation pattern of two parallel dipoles for the following cases where we have D as lambda by 2 and uh, Xi as 0, and the other one is D as lambda by 4 and Xi as pi by minus pi by 2. So we have to solve it for two cases, and we had derived the element factor and the array factor, and hence the pattern function for this two element array. And now this is the D which was unknown is given, and again the uh, the chi or the xi is also given. So from the previous six questions, yeah, this was the array factor, and we can substitute the array factor expression over here, and then we can calculate uh, this term. So if we calculate this term for the first case, which is d is lambda by 2 and this xi is 0, substituting that we, so putting d as lambda by 2, so and beta is 2 pi by lambda into lambda by 2, we end up with pi, and this particular thing is 0. Putting beta d as pi over here, this thing is okay. This will be this is just phi over here for the coordinate angle, and then this is 0. So we end up with cos pi by 2 cos phi. So we have got the array factor now. And yeah, so this pattern has its maximum at plus pi by 2, like this visible. So this particular function will become maximum when this particular phi, if phi becomes pi by 2, this cos will become 0, and this when this thing becomes 0, the argument to this cos will become 0, and then we will so this function will give us 1. So 1 is the maximum value which this cos function can achieve, and this will be 1 when the argument is 0, and the argument will be 0 when this cos is 0, and this cos will be 0 when this phi is pi by 2. That's why pi by 2, this pattern is achieving its maximum, that is in the broadside direction. So this particular rotation over here gives the phi, and at, this will also achieve maximum at minus pi by 2 as well, right? So at plus pi by 2 and minus pi by 2, pi equal to plus and minus pi by 2, we are achieving maximum. And if you just take the value as this cos phi as 0, if this phi is 0, then this cos phi becomes 1, and when this cos and the cos phi becomes 1, the argument to this cos becomes pi by 2. So cos pi by 2 is 0. So we at for phi equals to 0 and pi, this particular function gives out 0 values. So we have at phi equals to 0 over here, and phi over here we have 0 magnitude. And if you like calculate it for different phi values, this is the pattern that we will achieve. So we have the elements locations over here, and we are now radiating in the broadside. So this type of arrangement is known as broadside array, and the broadside pattern is shown in this figure over here, the first figure. Yeah. So this was the pattern, and is what you achieve. And since the excitation in the two dipoles are in phase, the electric field adds in the broadside direction. So what we're trying to say is the individual patterns, for example. So in this direction, like the elements were radiating. So each of them had a pattern looking like this, which might overlap. So in at this particular point, uh, what happens? For example, this the first element is over here, the other element is over here. Uh, yeah, and at this point, when we calculate the electric field due to this element and the first element, and due to the second element, they add destructively over here, and so we get a 0 value in this direction. Oh, in this at this particular point, they add constructively, so we get a higher value, and similarly over here we get a lower value, and then we get a higher value, which like it adds up to this function, like this pattern over here. So this is a little tough to visualize, but once we have, for example, we've calculated this function over here, what you can do is just plot the pattern function from using this, and we'll get this H-plane radiation pattern. So I'll pause over here. Like if you have any questions on, we can discuss this, and then move to the second case where we have d is equals to lambda by 2, and uh, uh, yeah, what was this element? Xi, right? Xi s minus pi by 2. It's very tough to keep track. This is psi. This is xi. There's another one which looks like this. This is I think it's written as xhi. Then this is phi, and this is theta. Okay. Um, any questions on this? I'll just pause over here for some. So, on a side note, did everybody use the link which I posted in the WhatsApp group? Like, was that working? Or did you join from any other link or the calendar invite? Can I do a poll, maybe? I'm guessing the link worked.
Yes, sir, link is worked.
Okay, thank you. Yeah, so I figured out the thing which was creating trouble. So apparently each class has its own, each meeting has its own link. So if you join via the calendar invite, you're directed to the correct link. But if you use any other link, so you end up being in a lobby. So I'll try to post the updated link before each class.
Yes, sir.
Yeah. Um, So I think this is pretty much straightforward, right? If you face any trouble, we can discuss this again. So essentially, what we have done is we are trying to calculate the electric field at this particular point based on the effects of these two elements. And once we got the electric field, we like just took the magnitude and formed element factor and array factor, and the element factor was previously the pattern function. But now this combination is the pattern function for the array. So that's what happened. So we found out the total electric field due to this configuration, and due to this configuration, uh, we just remove the common magnitudes part, and then the element factor and array factor together form the pattern function. And what we have seen is uh, the array factor is dependent upon this d and the phase terms uh, xi over here. And once we have the values for d and xi, we can just plot the radiation patterns. So that's what we did here. We just substituted the values in uh, the array factor, and we obtained the expression, and then we can just use maybe MATLAB to plot this. So it's not like it's not a very difficult thing to do. I think I'm just sharing one of these screens. Okay, just let me just do a quick Google search and I'll share the screen again. So okay, maybe later. Um, let's see the screen. So we discussed the A part. Uh, let's discuss the B part where we have D is equals to lambda by 4 and this I equals to minus pi by 2. So we have this expression over here. We just substitute D is equals to lambda by 4. For lambda by 4, this beta D will become pi by 2. So this will become pi by 2. And we have xi as minus pi by 2 over here. So we substitute minus pi by 2 over here. So this becomes, yeah, so this becomes pi by, so this is cos, we had a half over here. This is pi by 2 over here. We have cos pi over here, and we have minus pi by 2 over here. Okay, so this will multiply to give us cos pi by 4. Okay, so this half was multiplied to this element as well. So that's common. So this becomes pi by 4, and then we have, so we took out this pi by 2 outside, so we get pi by 4, and then we have cos pi and minus 1. Yeah. So we end up with cos pi by 4 and cos phi minus 1. We just took the pi by 2 terms outside of the this bracket. This is the array factor now. The, sorry, the pattern function. Okay, this is h thing. So this particular function has its maximum at this when this phi is 0. When this particular this phi when this phi is 0, this cos will become 1, and when 1 minus 1 gives us 0, and when this is 0, this particular argument will become cos 0, and cos 0 is 1. So we are getting the maximum value at phi equals to 0, and at phi equals to pi, when so this cos pi becomes 1. When this cos pi is 1, we have uh, yeah, at cos pi equals to 1 gives us minus 1, I believe. Yeah, cos pi gives us minus 1. So minus 1 gives us minus 2, and This pi by 4 into minus 2 gives us minus pi by 2, and cos minus pi by 2, this outside cos minus pi by 2 gives us 0. So we get 0 at uh, phi equals to pi. So now the pattern function has the maximum in the direction along the line of the array. Okay, so at this phi equals to 0, we have, so this direction is 0. Over here we have the maximum, and over here we have the minimum. So it will kind of look like this, look like an apple. So this is the pattern function. You can use MATLAB to plot this thing as well. Just vary the value of phi from 0 to pi or 2 pi, and then this is the pattern that we achieve. So now, since this is in the direction of uh, the, uh, uh, the elements, this is known as an end fire. So this is the end, and we are firing in this direction. So this is the end fire. And over here, we were radiating in the broadside of the element. So the element was arranged in this direction, and the radiation was in this direction. So this was broadside, and over here, this is in this direction. So this is end fire. So these are the two array configurations, broadside and end fire. And so this problem was for two elements. We can have more than two elements as well. And there's an explanation of how, uh, for example, the pattern due to these two elements, right? So both of them have some individual pattern over here, and they're adding constructively in this direction and destructively in this direction, and somewhat constructive, it increases in these directions. So we are ending up with a pattern looking like this. Yeah. Let's change color maybe. So yeah, so we are getting constructive uh, addition of the patterns here and destructively here. So, and this keeps increasing in magnitude in this direction. So we end up with the radiation pattern which looks like this. So hence that's what's written over here. So this we get an end fire array. So I'll pause over here. Maybe if you want to take a look at this expression or go through this paragraph, uh, please feel free to ask any questions that you have. Okay, so no questions. So this was pretty much similar to the, the first case as well. In both the cases, we just took the uh, R factor and substituted the configuration values in the and psi, and we got the expressions. So this is another question from the textbook. This is yeah, this was example 7, 11.7. This will be 11.8 from the textbook, but I'm leaving this as assignment for you to go through. But we'll briefly discuss this. In this particular question, we have been asked to discuss the radiation pattern of a linear array of three isotropic sources. So in the previous problem, we had two isotropic sources. Now we have three isotropic sources, which are spaced lambda by two space apart. So there are so this is the configuration. So we have three sources over here, and they are at lambda by two spaces. And the excitation now they are in phase. So it's basically xi equals to 0, but they have the amplitude in the ratio 1 is to 2 is to 1. So uh, the amplitude of this array, this element is 1. Over here it is twice, and then it is again. So the electric field over which we get at a far distance would be some even uh, yeah um, the electrical that we'll get is E1 plus E2 plus E3, and the if you write them, the magnitude for example, if the magnitude is EM, so this is will be EM some things plus 2 EM other coefficients plus again EM, but it will have other terms as well with them. So this is the problem, and then we have to solve this. So one of the ways that we can do is we can uh, so we have already calculated the uh, for the element part the array pattern for two element array, right? So we have done this where we have two elements as one, and with both of them have similar same excitation and magnitudes, and they are in phase. And what we can do is now we can split this particular element into two elements having one and one magnitude at the same point. So this pair and this pair are actually cascaded arrays. So we can take them as we can consider them as array of arrays if you follow. Um, so this particular array and then this particular array, they are they. So we can treat this particular system as these two sources, and this array has one element and this array has one element. So now we have two elements which themselves are individually arrays. But we have the array, we have the pattern function for this configuration, this array. So taking that as the element uh, uh, function, we can calculate this. So if you go through the example, it's written very in detail in the textbook. So if you solve it, we solve it, we get the this is the electric field that will turn out to be. So if you vaguely if you see this was EM 2 EM and then EM, so which results in a total of 4 EM, and then the array factor is actually just multiplied uh, from the two elements. So just refer to the textbook. The math is done over there, and the pattern would look something like this. This is for the previous problem. This was only the artifact, the pattern function that we got, and now this becomes just squared. So the earlier one looked something like this, and if you square this particular function, this just becomes taller like this. So this is the radiation pattern that we uh, get for a broadside binomial array. So a binomial array is basically like 1 to 1 or 1 to 3 to 1. If this is like uh, this can be even longer, like 1 2 3 4 3 to 1. So this is a binomial array. So I'll pause over here if you for you to just go through this question. This is left as assignment, so we won't do the math in this class. I'll just but the solution is also available. So this is example 11.8. You can go through the textbook for further detail, or if you want to try it out with pen paper by yourself and then refer to the textbook, it's up to you. Need not return the assignment. Okay, so no questions. We'll move forward. So we are halfway through. We'll now start with uh, general uniform linear arrays. So the till the previous slide we were just discussing two element arrays, and now with the discussion from two element arrays, we'll generalize it to form like general uniform linear arrays, and then after this we'll just briefly discuss uh, um, non-uniform or other sort of arrays. So if there are any questions from the previous slides, just you can write them in the chat or raise your hand. We can discuss that as well. Okay, so we will now consider an array of identical antennas equally spaced along a straight line. So just refer to this figure over here. So we now over here we have like n minus one, sorry, n elements. So we're starting from 0 and going up to n minus 1, and they are equally spaced. So this is d distances. So in practical cases, the spacing could also not be same, but for simplicity and for like if we have this as equal spaces, we'll be able to uh, like at least solve the problem in a more simpler, straightforward way. So for now, these are equally spaced, and we have the even the phase shifts are in the arithmetic order. So this is 0, this is xi, this is 2 xi, and this goes on. Okay, so each element is spaced at a d distance and has a increasing phase shift of xi. And so this particular arrangement is known as uniform linear array. So this is okay, and since the antenna elements are identical, the array pattern is a product of the element factor and the array factor. So, from the previous discussion, all these elements are same, identical. Okay, so each of them will have same pattern function individually, and the array pattern is a product of the element factor and the array factor. So we have an element factor for each of these elements, and then we can calculate the array factor, and the product of the array factor and the element factor will give us the pattern function for this particular this entire array. So let's just we so the element factor is dependent upon the kind of element that we are taking over here. Let's just calculate the array factor. Uh, so we have progressive phase shifts of this xi over here, and this is at a so there's a separation of d. Um, let's just write the array factor. So this is how the array factor would look like. Um, it- just take it. So from the previous example, if you remember, where we had some magnitude terms over here, right? So there was some magnitude terms, and then we had 1 plus e power j xi term. Okay, and then we had actually multiplied and divided with e power uh, j xi by 2, and then obtained the cost terms. So let's not go there and just write the terms. So the first term gives us 1, the second term gives us e power minus j xi. The third term gives us e power j2 xi. So yeah, and so on. So this is the array factor that we get. So this is essentially we're just trying to write the superposition of the electric fields due to 0, 1, 2, 3, and then simplifying the d terms and everything that we did in the previous uh, for the two element. And now since we have more elements for the two elements, it would have been just these two elements, these two entries. Now since we have n elements now, so this will go up to j n minus 1. Okay. uh, so I hope everybody follows this. And over here, this psi is beta d cos phi plus psi. So this remains same as in the previous slides. So this is the normalized RA factor. Now, one thing that we can notice is this is actually a geometric progression, and we have one standard formula for geometric progressions, for the summation of geometric progressions, and this is something like this. So this is high school mathematics. If we have 1 plus a plus a square, and similarly this goes to a n minus 1. So this will be given by 1 minus a power n by 1 minus a, something like this. So this is geometric progression, and we can just summarize this expression over here. And once we have this expression over here, what again the for the numerator term, again what we can do is take uh, um, e power j n psi by 2 common, and so the inside will be left with e power minus j n psi by 2 minus e power j n psi by 2. And if we multiply divide by 2, this actually resembles sine, so this will become 2 e power j psi by 2 into sine n. Okay, this will have n as well. Sine n psi by 2. So this, yeah, um, very poorly written. So essentially, so this numerator will become 2 e power j n psi by 2 into sine n psi by 2. Similarly, the denominator will also become 2 e power j psi by 2 sine psi by 2. And all of this is inside mod, right? So this is inside mod. So e power j n psi by 2 and e power j psi by 2, their magnitude is 1. So they disappear. And we can just cancel these two. So we'll end up with this final expression 1 by n sine n psi by 2 divided by sine psi by 2. And this is a dimensionless quantity which is known. So I'll just pause over here to I've tried to write down the steps over here, which I did not do very successfully. I'll just pause for you to try to solve it yourself, or maybe go through what I wrote over here. If you have any questions on this, you can ask them. Also, if you have any, I hope you will follow this. Any questions on 1187 or 1189? Yeah, please ask them. Okay, so we'll proceed. So now we have found out the array factor. Um, is any questions?
Yes. The difference, what is the difference between the uniform linear arrays and the common linear arrays?
Um, there was some noise. Can you please repeat your question?
So, what is the difference between the uniform linear arrays and the linear arrays?
Okay.
The
So the
distance.
unit. Yes, please continue.
So the distance should be same in the uniform linear arrays. It is kept d every time.
Uh, yes. Two parts to the uniform linear arrays are the distance between the arrays, the elements that has to be constant, the spacing d, and the other is the magnitude of which is which from which we are exciting. That also has to be same for each element. Okay, so we are giving some particular magnitude to each element that has to be equal for all the elements, and then the spacing should also be equal. So that will be a uniform linear array.
Okay, and sir, also I have a one question. What is xi actually? It is totally related to the phase shift, or I don't understand about the significance of xi.
Okay. Yeah, this is the phase shift between the excitation between each element. So so if you worked so if you, for example, if you have these elements, right, and then you have to feed them some excitation, we have to feed them some power. So what you're doing is uh, giving some maybe some sinusoidal signal to uh, each element, right? And this, for example, this you're feeding them some voltage V naught sine omega t plus some phase. Okay, we're giving them some phase. So the phase for each of them could either be equal. This could be phi for all the elements, or it could be phi 1, phi 2, phi 3 for the different elements. And the difference between these phi elements, for example, if this is phi 1, or phi 2 would be phi 1 plus psi. Uh, uh, Phi 3 could be phi 1 plus 2 xi, and similarly. So there is some phase shift between, if there is some phase shift, this is represented by this element xi over here. And if this becomes 0, then all of these are being fed with the same phase signals. Um, um, was I able to make this clear? Any follow-up questions, Shipra?
No, sir, thank you.
There's another question by Sarila. Yes, please um, unmute yourself and ask me the question. Or
So I wanted to know whether is there any standard value of psi when designing of the uniform arrays?
no such standard values. Uh, for usually what we've seen for broadside radiation, this is usually 0, and based on for end fire, this could this there is some constant psi, and this could be different for different and array formations. And for example, if you want your maximum, okay, so for example, if this is arranged like this, right, and you want a broadside rotation, this psi is equal to 0 will give you broadside rotation, and for some value it will give you uh, if this yeah, so this will give you an end fire rotation. And if you vary use different values, it probably will give you some radiation in some other directions as well. So you can basically tune the beam in different directions using by varying this phase value. So no standard value for array, it could be different values, and this has to be optimized essentially when you're designing array or a phased array. This xi value will change. Any follow-up
And the
questions
value
on that?
for D and the value of D also.
Yeah, the value of D also has to be optimized. For
Okay.
uniform linear array, the D value is equal for different between these element spacing. You it could be lambda by 2 or less than lambda by 2 or greater than lambda by 2 as well, based on how the pattern you want. This D can be changed and optimized. Yeah, so that can also be optimized, and also it need not be like we'll see later. It need not be even same. We need not even have the same distance between the elements. It could also be different D. Like it could be D1, D2, D3, and then you'll achieve a certain desired pattern. So all of these can be variable to achieve like a desired pattern function. Any follow-up question? Was that clear? Any questions?
Yes,
Follow-up
yes. So,
questions?
sir, can you discuss any one example with the different values of D? Uh, it could help us to
Uh,
know what kind of the things, relations, patterns we can get.
Okay. So at I think at the last slide or the second last slide, we have some text. I had removed the references. So in this particular chapter, if you go to the general uniform linear arrays, in just before the last paragraph of this particular section, there's a in that paragraph they have referenced different papers which have different values for D or different phase values. So these problems themselves. So if we change the value of D, like the spacing between different elements, the math will become very complex. That's too much for this particular class. But if you want to just look at the results by for different D values, you can just refer to those papers. The textbook has them in the reference. Um, so you can do that. So like if we have, for example, different D values, if this is D and this is D2 and this is something else. So the pattern might change, look something like this. Okay. Or and if you tune them properly, you could get some very nice. Let me just change this color. Uh, Back to red. Um, so we might end, for example, if we want a certain radiation pattern, let's look at this circle over here. We want a radiation pattern which looks like this. Like it radiates in some theta and phi angle in some direction, and it has a maximum over here. So what we need to do is we need to tune the this psi values and the D values, and this will help us achieve this particular radiation pattern. So for that we need to like use HFSS or CST or do pen paper stuff, and then you can achieve that value. But using pen paper will be very difficult because you will have each electric field adding up like differently. Like all the approximation, for example, using this formula for geometric progression, this won't hold up because each of these elements will now have different magnitudes, and even these coefficient terms will also not be same because they are same because we are assuming uh, this particular thing is we have a constant shift between elements. So we won't be able to generalize using this array factor. So the array factor will also be very complex. Uh, we're able to follow that. Like doing an example in the class is too much. I'm just giving you an idea. To get a particular desired pattern function, we might have to tune them individually. So you can refer to the textbook. By the way, I can tell you the page number from the book which I shared. So let me reshare the screen. Okay. sharing. Share this. Let me share the screen. Which, yeah, okay. I hope you are able to follow this. Uh, can you see the screen? I'm sharing a textbook. Hello.
Hello. Yes, sir.
Yes. Can you see the textbook I'm sharing?
Yes, yes. Yes, yes.
Okay. So if we go to here, this is transmit and receive system. Okay. Yeah. Just before this particular receiving antennas. Okay. Just before this, page number 631. Okay, page number 631. Um, you can see the references 1 to 4, 5. I like them, right? Yeah. So there are these references um, which are there in textbook. So these are on non-uniform arrays. You can go through these references for your like for a better understanding of uh, non-uniform arrays. Page 631. 61 TK Cheng. So I'd shared the textbook in the group as well. Like if you have not received it, let me know. I'll reshare it. Any other
Okay.
question? Um, any other question? Anyone? Sir, any follow-up questions? I
No,
see
sir.
your hand is still up.
Yes.
Okay. 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 So then we'll proceed. We have we in the previous slide we derived the array factor for general uniform linear array. So this is what we had as the arrangement where you had n elements, each of them with progressive phase shifts xi and this separation d. And we wrote down the array factor and used the arithmetic sum of the geometric progression to get this expression over here. We then simplified the 1 minus e power uh, j uh, psi term to give us e power j psi 2 divided by 2 and give us sine psi by 2. Yeah. So this simplification we did and we got this particular expression over here. And now this is the general expression for a normalized array factor. So we're saying normalized because we have this 1 by n term over here. So yeah, essentially, since we are just concerned with the pattern, right? So we're not very focused with the exact magnitudes, like term. We're happy to know which direction we have the maximum radiation, how the pattern is, and the all the parameters such as the beam width or the nulls, all of them can be calculated with the normalized expression. So 1114 is the sketch of the normalized array factor for a 5-element array. So for n equal to 5, we have this is the uh, normalized array factor plotted over here. So this is how the array factor looks like. So starting from 0 to 2 pi. So this is the in the Cartesian coordinate. We had discussed in one of the classes that we can either plot them in Cartesian coordinate or in the polar coordinate. If we do that, the polar coordinate will look something like this. More like, yeah. So a major lobe and then a smaller lobe like this is how we get, yeah. And then this would be 0, and then this would be pi, this direction if you're moving pi. Sorry, this is against psi. Yeah. So this is how the we're plotting this array factor against the psi value over here, and the actual radiation pattern is a function of okay, this should be psi. Function of psi depends on the values of beta d and xi, which we have seen. Okay. Based on so we plotted this from 0 to 2 pi over here, and this can be uh, as phi varies from 0 to 2 pi. So we yeah the expression for psi was like this: beta d cos uh, phi sine theta plus uh, xi, right? So this was the expression, and as this this phi varies from 0 to 2 pi, the value of xi will change. Sorry, the value of psi will change, and based on that, we it changes from, for example, so if this is 0, this yeah. So based on this phi value, it will vary from beta d plus phi plus psi to minus beta d plus psi, for theta equal to pi by 2. Okay. So for theta equal to pi by 2, and for 5 different pi values, it will vary from minus beta d plus psi to beta d plus psi. And based on that, we can plot this figure over here. And from this particular radiation pattern, we can uh, calculate the different parameters that we had discussed, I think, in the first or the second class, which were like the direction of the main beam and the uh, beam width, location of the nulls, yeah, the side lobe levels, and the magnitude of the uh, the magnitude of the side lobe levels as well. So let's look at them one by one. So the first one is the main beam direction, and the maximum value occurs when the psi is equals to 0. So if you look at this function over here, okay, so this is your uh, pattern function, right? And the maximum value of this pattern function is achieved based on this expression inside. And this particular this function achieves its maximum value when the psi value is 0. So you'll just have to take my word for it. This is like, for this particular function, you have to use on the limits and stuff for nx by sine x, and then calculate the uh, limits for like for x, and essentially, if you do a derivative and solve it, you'll find out this achieves its maxima at x equals as x tends to 0. So at psi equals to 0, we get the maximum value of this pattern function and the array factor. And yeah, and for this equal to 0, so we had psi equals to this beta d cos phi and sine theta. So we're taking theta equal to pi by 2. We are plotting the H field patterns. H pat uh, so H plane, yeah, H plane, and for that theta equals to pi by 2. Yeah, so theta equals to pi by 2, and we have b and this psi value is 0. So beta d cos phi plus xi equals to 0, and which leads to cos phi not equals to this expression over here. And this is yeah, and now this is very general, right? So we do not have the values for these two things. So we can take two special cases. One is the broadside array, and once we have said that this is a broadside array, we know that the max the direction is for a broadside array is like this, right? So the maximum occurs when phi is equals to pi by 2 or minus pi by 2 plus minus pi by 2. And for broadside, uh, for broadside, if this is equals to pi by 2, so for and yeah, so we substitute this pi by 2 over here. So for cos pi by 2, we have this is a g, so this means this is 0, which implies this xi has to be 0. Okay, so broadside for broadside array, this should be excited in phase. So this means all of these elements will have the same phase. It could be 0 phase or like whatever. So all of them should have, for example, if they have some 5 1 values, so all of them will have some 5 1 values. So they have to be in phase for broadside. Um, was this clear? Do Should I repeat this once again? So what we're trying to do is we're trying to find out the main beam direction, and the main beam occurs when this array factor has the maximum value, and this happens when this psi value is 0, and for psi value equals to 0, we equate this function to 0, and we end up with cos phi equals to minus xi by beta d, and for broadside array, we have the main beam in the main beam at phi equals to pi by 2, and substituting that over on this expression, we end up with xi equals to 0. So this means that for broadside array, the xi has to be 0. And if xi is 0, it implies that all the elements are excited in phase. Okay, so I'll pause over here. Any question? Like, was this clear? Any questions on this? Okay, so no questions. Will proceed. We only have a few more slides to go, I think. So this is slide 18. Oh, we have quite a few slides. And for the end phi array, the main beam is in this direction over here at phi equals to 0, and for phi equals to 0, this implies um, this implies we have this expression over here, and phi equals to 0 implies BD is equals to uh, this. Yeah, the xi equals to minus bd, just put 0 over here. So this will imply xi equals to minus bd. So for so to get a yeah, so for end fire array, it could be it could these the phase shift depends upon the product of uh, your wavelengths. So this is 2 pi by lambda and your separation d. So based on the product is how you can design your end fire array. So I'll just pause over here for like to look at uh, the results that we obtained. For broadside array, we got xi equals to 0, and for endfire array, we got xi equals to minus bd. So, and this was satisfied in one of the examples that we saw earlier in this class. Okay, so we'll proceed with null locations. Um, So the array pattern has null when this particular function becomes 0, and this becomes 0 when the numerator becomes 0, and the numerator becomes, so sign becomes 0 when it is equals to plus minus k pi, and k being 1, 2, 3, 4 this elements. So n psi by 2 is equals to plus minus k pi gives you the null locations. So this is pretty straightforward, and yeah, so this is the expression for null location, and we cannot further simplify this because we the psi itself is dependent upon beta d cos phi plus xi values. So based on broadside or end fire or those things, we will get the expressions for this xi values, and then we can calculate. So yeah, so we have the null locations with us. We just need to make the numerator 0 over here. Similarly, width of the main beam. So we calculated the location of the first nulls, right? So once we have the location of the first nulls, um, we can just the first null is given by n psi. So the size location of the first null, and psi by 2 equals to plus minus pi, which implies psi will be equal to 2 pi by n. And in order to see how this psi converts to an angle between the first nulls, we need to know the direction of the main beam. Okay, so again we get back to the problem of broadside or end fire. Or so if we take the broadside array, so we have the psi value and the phi value. So we'll substitute that in for xi, and the main beam if and the yeah the beam width uh, is between the first nulls, which will be 2 phi given so the phi naught is the main beam. So for example, if we have a radiation pattern for broadside like this, so this is phi 0, and this is the first null at phi 0 1. And so the difference between this angle is basically delta phi, and the twice of this will give you the beam width uh, between the first nulls. So cos phi 0 1 is this expression over here, and they can calculate delta phi as sine inverse of lambda by n. So essentially, we're just substituting the values for psi over here. Okay, so this gives us the broadside array. As similarly, we can calculate it for. So I'm rushing a little bit over here. We can go through the slides. So it's essentially just doing step-by-step maths. If you have any follow-up questions on this, we can discuss. Similarly, for end fire array, we have the xi value and phi values. and we just substitute that the expression over here, and we end up with this expression which cos phi 0 is essentially we have this end fire thing, right? So this particular angle is phi 0 1 we have where we have the first null. So we're calculating the width of the main beam, which is so we need this phi 0 1 value over here, and we have this expression. Yeah, and then we need to we need to calculate this. We got this expression. We substitute the phi values over here, so we get 2 pi by n beta d. Uh, yeah, and beta over here is 2 pi by lambda, and just solve this, and we end up with this expression. And just we to calculate phi 0 1 now over here, we just take cosine inverse of minus lambda by n d, and we end up with this expression over here. So this is uh, yeah. So cos phi 0 1 is all equals to cos delta phi, which is uh, 1 minus delta square by 2 for small theta. So this is some trigonometric approximation. So we get delta square by delta phi square by 2 equals n uh, is equals to lambda by nd, and just solving this it gives us this expression. So if we compare the beam width of the broad side, which is this expression over here, and this is for the end fire. We see that this end fire is actually greater. The beam width of the end fire is greater than the broad side. So that's one observation. It's how this essentially this you can write this as root over 2 and root over lambda by n d, and we know that um, nd is actually greater, much greater than sorry, lambda. So this is actually a fraction, and root over fraction is so if you take root of a fractional value, it kind of increases. Like, I guess this is how this looks like, or it looks like this. Yeah. So fractional value, if you square them, it becomes greater, and then this is root 2 times. That's so essentially the end width of the main beam for end fire is greater than the broadside for the same length. Okay. Um, to find out the side lobe locations again, side lobes are actually the minor maxima that occur approximately when the numerator on this thing is maximum. So so these value. So for nulls, what we did was we equated them to k pi, and for um side lobes, we'll equate them to k plus at, okay, so 2m plus 1, basically the odd multiples of pi by 2. If you equate them, you get the side lobes. If you equate them to multiples of pi, it gives you the nulls. So this is the first side lobe occurs at minus 3 by 2 pi. It doesn't occur at pi by 2, because if you remember, the first null is actually at plus minus, and the first nulls are at plus minus pi. So this particular value lies inside the first major lobe. Okay. So this is how we get the side lobe locations. Yeah, so this is the location of the null. So the first null occurs at plus minus pi. Hence, this implies that we cannot have a side lobe at pi by 2. The first side lobe maxima occurs at 3 pi by 2. And so there is some calculation in the textbook calculating the first side lobe level value. If you substitute the value for psi this phi value over here. This will give you some result. So this is the math that ends up, and uh, with some approximations we get this value 0.212, and this is the side lobe level, and this is almost independent of n as long as n is large. So you can go through the derivation in the textbook as well. I'm trying to wrap up the class within time. We have already exceeded the 5 p.m. time. Um, yeah, so if you just go through the textbook, and you'll see that we end up with this particular value. So this side lobe level value remains same as long as n is very large, and this is 0.212, or my or 13.5 dB down from the principal maxima. So if the principal maxima is at 0 dB, the first side lobe will be at minus 13.5 dB. And side lobes are actually a concern, and we want them to be even lesser. So there is Yeah, so there is another example in the book, which is example 11.9, which is again left as assignment. Over there, there is the exam which we discuss how to reduce this side lobe level. So in the previous example, we had seen this kind of power the the feed, the excitation of was taken as 1 to 1, right, in one of the uh, examples earlier. So this is the tape where we taper the excitation of the different elements array. So for example, if we have 5 elements, we were seeing examples of 5 elements, right? So 0, 1, 2, 3, 4, and we were giving them equal power, and that gave us side lobe level of 13 dB. What we can do is we can give them different elements power is 1, 2, 3, 2, 1, and this will actually, if we give them power like this will actually reduce the side lobe level significantly. So the solution, you can refer to the textbook, but for your knowledge, the side lobe level upon giving power in this fashion gives us is achieved to be 19.2 dB. So which is like 7 dB, so almost 7 dB improvement uh, from the regular power distribution. Okay. I think we have a few more slides. Yeah, so I'll give you an overview. So in general, we were discussing uniform linear arrays. So this was what I was talking about from the textbook, where we had references from 1 to, I think, 5 or 6 references were there. So all those references. So for our discussion, we were using uniform linear arrays, but these arrays need not have same d distances or xi excitation, or it need not be even be linear. So to get a particular sort of pattern, like for example, if you want 3 beams, or if you want 2 beams in other directions, and you want a null in this direction, or like to engineer the kind of radiation pattern, or you will have to modify the arrays, and modify the phases and the spacing between the elements. And so there are different examples out there. You can go through literature, and so that's what this page is about. So it need not be same. What we did that to simplify the maths that we want to go through. And um, another thing is that we discussed linear arrays, right? So we had linear arrays like this. So, and what we can do is we can arrange the linear arrays in the other direction as well, and form 2D arrays. So we can also have 2D arrays, and we saw that by changing the xi value, we were able to move this radiation in maximum radiation in the broad side to maximum radiation in the end fire direction by just changing the this uh, this xi value. So this implies that so if we have so by tuning this xi value, we can what we can do is um, get maximum radiation in one of the directions, and if we are able to change this in real time, about we can also perform beam scanning. So this maximum radiation direction could move from one direction to the other, and we can scan this area. So this is a very useful thing. And if we had a 2D array like this, so we could scan this region in 3 dimensions. So this implies that we can have some phased arrays stuff, and we can also have scanning. And since this psi, right, the psi is a function of psi is a function of theta and phi. And so based on by varying this theta and phi in 2 dimensions, we can scan in both elevation and azimuth directions. Yeah, so that's so I rushed through the last few slides. So I'll refer you to please go through the textbook. I'm sorry, we ran out of time. We kind of like short on time on today's class, and there was a lot of material. But we did discuss the two element arrays and the general uniform arrays in detail, and then uh, and we discussed the n element arrays, and then we just started with the different properties such as main beam, side loops, nulls, the yeah, beam width, and different parameters. So all of them are basically, once you get the array factor, you're just imposing different constraints on the array factor and to achieve the to get the values. So that's all for today. So I have to like leave early. So I won't be taking any questions right now. So if you have any questions, please feel free to reach out to me in the WhatsApp group or via email if you want to ask a question personally. So that's all right. I'll share the share the slides now, and share the recording in a couple of hours by midnight. Yeah. So thanks for joining. Sorry for rushing the class towards the end. Um, yeah, please feel free to reach out to me if you have any questions on this, and if you have any questions from the textbook. Okay. Yeah, thanks for joining.